We are going to do a quick review of our theoretical and experimental probability from yesterday, and then we're going to talk about compound probability. So we're going to talk about what is the probability of this and that, or the probability of this or that. So probability of multiple events happening at the same time, or looking for either event to occur. So thinking back to yesterday, we talked about theoretical and experimental probability. How did we find probability in general? How do we calculate the probability? Alex?
Number of desired outcomes over number of possible outcomes.
Good. We looked at what we were looking for. So what was that desired outcomes? How many desired possible outcomes did we have? And then how many total possible outcomes entirely did we have? So it was number of desired outcomes divided by number of total outcomes. So if I were to find this probability of getting a number that is greater than 4, what would my probability be? So what would our probability be of getting a number that's greater than 4 on just a normal 6-sided dice? 2 out of 6. My two numbers that are greater than 4 are 5 and 6. So I have 2 desired outcomes out of 6 total outcomes, which if we divide that 20.3. Typically we like to keep our answer as a decimal, but a fraction is still fine for an answer. Colton, do you want to take your hood off for me, please? Can you please? Thank you. So that was our theoretical probability. That's what should occur if we were to roll this dice. We should have a 30% chance of getting a 4 or greater than a 4, I'm sorry. Now we're going to look at the experimental probability. So I took a dice and I rolled it 12 times, and these were my results that I ended up with. So I want to see, based off of this experiment, what was the probability of getting greater than a 4. So we'll still remember the same thing, getting a number that's greater than a 4. What would our experimental probability be based off this chart? So we rolled it 12 times in total, and then we have the frequency of each number. So I rolled a 1 3 times. I rolled a 2 once, and a 3 once. 2, 4. How'd you get 5 out of 12?
Because they only roll 5 and 6. Like 5 and 3 times and 6.
Good. So 5 and 6 are still our numbers we're looking for. Those are still our numbers that are greater than 4. 5 showed up 3 times. 6 showed up 2 times. And so together we got 5. So we have 5 results that were greater than 4 out of 12 total results. And so our probability of 5 or 12, we can do that divide or the division, and we should get roughly 0.42 as a probability. So our experimental probability and our theoretical probability didn't really match up for this, and that's okay. Not every time, or not all the time, should your experimental and theoretical be exactly the same. Sometimes it might, sometimes, but it's not always the case. We don't live in a perfect world, so it won't always happen. Yeah, you can put it as a percentage. Once again, a fraction, decimal, percentage, they all equal the same thing. It's just different ways of writing it. I personally find it easiest to work with decimals, so that's why I keep it as decimals. But if you like percentages, put it as a percentage. If you like fractions, put it as a fraction. I just typically write with them. But yeah, it's okay for the theoretical and experimental probability to be the same. I could flip a coin 200 times and make it all end on tails. It's unlikely but possible for an end result. So these might always be a little bit different because we don't live in like a perfect, probable world. Chances aren't perfect. And so sometimes you will get different results. Are we okay with this from yesterday? So today we're going to talk about, once again, we're going to look at compound probability. So we're going to look at what is the probability of this and this both occurring at the same time. Or what is the probability of either one of those occurring. So we're going to look at these compounds. And so we're going to still use our theoretical and experimental probability that we've seen before, but now we're going to use it and sort of help sort of do more difficult situations or more difficult probabilities. But before we start off, I want someone to look up the temperature from Mount Victory for tomorrow, and then I want someone else to look for the temperature for San Diego tomorrow. So we want to find these two temperatures. Temperature for Mount Victory and temperatures for San Diego.
I don't know.
So let's see what these results are going to tell us. Just the high.
Okay. So for tomorrow it's a 69.
For San Diego? So San Diego has a high of 69. Okay. we have Mount Victory. Floating. I think the other classes.
It's like 40 something.
I think it's 64. It should be somewhere around there, I think, if you were to check your phone or something. Or if it were to load. So we have 64 for Mount Victory, 69 for San Diego. Are these weathers going to affect each other? Are these temperatures going to affect each other? No. So we have San Diego's like all the way across the country. Mount Victory is in California, right on the west coast. San Diego's on the other side of the country. Mount Victory's in Ohio. For just tomorrow, they won't affect each other. Potentially, San Diego might have a storm that might blow over to Mount Victory if it was strong enough. But for tomorrow, these temperatures are not affecting each other. The temperature for Mount Victory tomorrow isn't affected by the temperature for San Diego tomorrow. So when we have two things that do not affect each other, when we have two situations that are not sort of related, they aren't affected by the other, we call these independent events. So two events that are independent are completely separate. They completely don't affect each other. So I could flip a coin and then roll a dice. They're completely separate. Whether I land on heads or whether my coin lands on tails will not affect what number I get on that dice. They're completely separate events. They shouldn't have any impact on the other one. And so that's an example of independent events. A non-example of this would be if I had a deck of cards. I have 52 cards in this deck. If I pull one card out, I now just change that deck to 51 cards. So if I pull another card out, that probability just got changed for that second card. Initially it was 52, but now it's 51. And so because pulling that one card out, pulling the second card out, or pulling the first card out changes the probability of the second card, that makes them dependent events, so they're affected by each other. But flipping a coin and rolling a dice aren't affecting each other. Whatever I'm doing over here doesn't affect whatever I do over there. The probability of me finding a red car in the parking lot isn't affected by the probability of Gabe being able to do a backflip. They're two separate events, two separate things. They're not affected by each other. Independent events is a big thing that they do on your state test. Probably out of all the probability questions on your state test that I looked through for a practice question, I would probably say maybe 60% of them are probably independent or have involved independent events, and they'll tell you these events are independent or something like that. So this is a big thing that occurs on your state test. And the reason why it occurs a lot is because when two events are independent, with the way we calculate the probability can be a little bit different. So if you have two independent events, the probability of both of those events occurring at the same time, probability of this and that, both occurring, not just this, not just that, but both of them occurring at the same time, is going to be the probability of the first event multiplied by the probability of the second. The probability of event A and probability of event B. The probability of both of these things occurring, all we have to do is just take their probabilities and multiply them together. Because they don't affect each other, we're looking at the chances of both of them happening at the same time, but it's just based off their own probabilities. So once again, flipping a coin and it landing on heads and me rolling a dice and it getting a 6 shouldn't affect each other. So it's just what are the odds of me getting a 6, and what are the odds of me getting a heads, I just multiply those two together, and that's the odds of getting both of them at the same time. Are we okay with this? So I could roll a 6 and get a tails, but that's not what I'm looking for. I want a 6 and a heads. Those are the only results. I could get a heads and a 4, but that's still not what I'm looking for. I need both those results. The probability of heads and a 6, once again, it's going to be the probability of getting a heads multiplied by the probability of getting a 6. So again, both those probabilities, multiplying them together, and that will be my total. What's our probability of flipping a coin and getting a heads? 1/2 or 0.5. If I foresee decimal group, okay with that. What's my probability of rolling a dice and getting a 6? 1/6 or 0.16 repeating, or 0.17 is what we use. We round up. So all we have to do is take these two numbers, multiply them together, and that'll be the probability if I flip a coin and roll. If I flip a coin and roll a dice at the same time, I get a heads and a 6. And it should be 0.08 8.85 is my probability for getting both. So 8.5% of the time, awesome, I'm going to get a heads and a 6. The other 91.5 times, I'm probably going to get something else. I might get a heads, I might get a 6, but I'm not going to get both of them.
Is that big proven?
What do you?
Like experiments.
You could, so once again, these are theoretical probabilities. We didn't roll any dice, we didn't flip any coins. So this is all using our theoretical probability, but you could do this with a experimental probability as well. You could flip a coin and roll dice a bunch of times, and you could keep going and keep going and keep going, and you should get a number that should be close to this. It might not be perfect, but it should be close to that, because that should be your experiment. And it's possible you could get that number, but that's what number you should arrive at. Are we okay with independent and how we calculated that so far? So once again, anytime two events are completely separate of each other, just multiply your two probabilities together. Now, typically we write it the probability of this and that. So the probability of A and B. But that's not always the case. And so sometimes they might use this funky little upside down U. We call this an intersection. It means the exact same thing. It's the exact same thing. It means and. It means where the two are sort of overlapping if they're independent, or in this case, where are the two like happening at the same time or when they occur at the same time. But it's just another way of writing it. Because mathematicians are lazy, so we didn't decide to, instead of writing 3 letters, we just decided to write 1. Because what? So I just want you to be familiar with this symbol because it's probably how they're going to write it on your state test. So rather than writing P and B, or A and B, they'll probably put A with that intersection symbol B. And so I just want you to become familiar with these. That way, if you see them on your state test, you don't freak out because you don't know what it means. So I'm gonna write them using these symbols or using that symbol. And so if you ever get confused what that symbol means, again, just let me know. Why that's that and, just so you get familiar with it, so you're used to it. If you would prefer writing and so every time you see one of those, you just change it to and, that's fine. It's just your way of remembering it. But I'm going to start writing them with that, just so you become more familiar with it. Okay with that? Just to help you on that state test. So we have a desk drawer. You open it up. You find 5 red pens, 6 blue pens, 3 black pens, 24 paper clips or 24 silver paper clips, and 6 white paper clips, all in this desk drawer or desk drawer. So you close your eyes, you reach in, you grab a pen, and you grab a paper clip. You pull it out. We want to see what is the probability that you pull out a blue pen and a white paper clip. What is the probability of reaching in, pulling out a blue pen and a white paper clip? Now, when I reach into this desk and pull out a blue pen or pull out a pen and a paper clip, does my pen, whatever pen I pull out, does that affect whatever paper clip I pull out?
No, it doesn't.
Now, because I'm reaching in for one pen, one paper clip, I'm not worrying about mixing them around.
But you have to get them on the same. Yeah.
So, but because I'm only going from one pen, one paper clip, they shouldn't affect. So those would be considered independent events. So once again, anytime we're trying to solve for the probability of 2 independent events at the same time, looking for that and, we can find the probability of one and multiply it by the probability of the other. So I can take the probability of getting a blue pen and multiply that by my probability of getting a white pen. So based off these results, and based off these numbers, see if you can figure out, okay, what is my probability of getting a blue pen? What is my probability of getting a white paper clip? And see if you can multiply these two together to get your probability of both of them. So see if you can do that. So looking at this question, we are looking, okay, how many blue paper clip, or what was my probability of getting blue paper clip? What was my probability of getting a blue pen and white paper clip, and then we wanted to multiply them together. So looking at our blue paper clips, what did we find for that probability? Blue pen, I'm sorry, what was my probability for that? 0.42, 0.43. It should have been 6 out of 14
I'm scared of that.
So we had 6 blue paper clips out of 14, or 6 blue pens out of 14 total.
Should we round?
I typically round to 2 decimal places. If you don't have to round to, so if you want to keep that whole number, you can, and because that will give you a better answer towards the end. But if you round to 2, that's probably, or round to 3 is that. So, how many white paper? What was our probability of getting a white paper clip? 16 over 40, or 0.4 is then our probability. So we had 16 out of 40 paper clips for white. All we have to do is multiply these two together, and we should have gotten 0.172. That might be a little bit different depending on whether you use those whole decimals or if you're rounding to 2 decimals. Are we okay with that? Once again, anytime it's independent events, anytime we're looking for that and, just multiply those 2 probabilities together as long as they're independent. So that was if 2 events are independent, whether they don't affect each other. Now we're going to look at a different situation. So let's say I have a 6-sided dice. I want to roll a 5 and a 2 at the same time. Is that possible? No. I can get, I would have to have 2 dice. I can get one answer, I can get a 5, or I can get a 2, but I can't get both. So if it's impossible for 2 events to occur at the same time, we call these events mutually exclusive. So if 2 events completely can't occur at the same time, mutually exclusive. For example, you can't be a senior and a freshman at the same time. You can be one or the other, or a junior or sophomore, but you can't be both. They're mutually exclusive. You're going to fall in one category, but you can't overlap into the other. So there's no overlapping between them. Does that make sense? How we come up with that? So if you're looking for the probability of both of those events occurring at the same time, if I'm rolling for the, if I'm trying to find the probability of rolling a 5 and a 2, it's 0. It's impossible to happen, so it's just automatically 0. So if 2 events A and B are mutually exclusive, then the probability of A and B is 0. No math. It's automatically 0, as long as you know they're mutually exclusive. Simple enough? Okay. And typically they'll tell you if 2 events are mutually exclusive, or they'll tell you if 2 events are independent for the problem.
Is a possibility
What?
happening? Of being a senior and freshman this side?
Shouldn't necessarily be possible.
It shouldn't be. It happens. People make them possible.
Okay. Now, so that was 2, or that was rolling a 5 and a 2. Now we're going to figure out, okay, what is the probability of rolling a 5 or a 2? Probability of getting this or that. I don't care if it's a 5. I don't care if it's a 2. I just want one of them. Add the probabilities together? Okay. So what's my probability of getting a 5?
Or 1, 6,
What's my probability of getting a 2?
2, 1, 6, yeah. Yeah, that's a 2, 6.
So they should be 2 out of 6. Well, if I think about this theoretically, I have a 5 and a 2. Those are my 2 desired outcomes. I have 6 total outcomes. So that should be right. So as long as these 2 events are mutually exclusive, and you're trying to find the or statement, you're trying to find this or that, then all you have to do is just add the 2 together. But once again, strictness on, they need to be mutually exclusive for that to occur. If there's some overlap, if it's possible to get this and that at the same time, then we start getting into a little gray area where we'll have to talk about that. But if they're mutually exclusive, if there's no overlap, just take the probability of that one, take the probability of this one, add 2 together, and you're solved. So the probability of getting a 5 is 1 out of 6, 0.17. The probability of getting a 2 is 1 out of 6, or 0.17. So the total should
Why
be.
is it 1, 6?
So 5 is my one number I'm rolling on that 6 out of 6. That's the one number I'm looking for out of the 6 options. 2 is my one number, I have one other number I'm looking for on the 6 options. So 2 out of 6 are the 2 possible answers we want to get, which if we divide that should be 0.3. Was that a little bit better of an explanation?
I mean,
Now, just because, once again, mathematicians can be kind of annoying and they can be kind of dumb and they can be pretty lazy, rather than writing 2 letters of OR, they changed it just to this U.
literally the exact same thing that they didn't make it.
So we call this symbol union. And there's more to it than they just decided to throw in a random symbol to it. We have these symbols already and they meant special things, but basically these mean the same thing. So if you're looking for the probability of this or that, it's the same as having A union B. I don't necessarily expect you to know the names of them. That's not as important to know the names of these symbols, but just knowing what they mean. So seeing that U means it's an or sign. Seeing the upside down U means it's an and. So I just want you to be familiar once again because those are probably what's going to show up on that state test. Are we okay with this? So let's look at an example. So we have this school with some student athletes at this local high school, but there's a rule. They can only participate in one sport per season. So you can't participate in baseball and track at the same time. You can only participate in one sport per season. So during their winter season, 28% of the students played basketball. 24% of the athletes played or were on the swim team. So we want to find the probability that if I randomly select an athlete from this school, what is the probability that I get a basketball player or a person on the swim team? Once again, it's a probability, it's an or statement. So it's a probability of playing basketball or being on the swim team. Yes. Or the probability of bus. So basketball or swim team. Once again, because they're mutually exclusive, because it's impossible to be a basketball player and be on the swim team at the same time based off that rule, we know it's just both of those two added together. It's just the probability of this plus the probability of that one. So if you have a percentage, in order to change it to a decimal, just put your decimal place 2 places. So it will be right here, so we go 1, 2. So it's 0.28 for basketball players plus 0.24 for swimmers. And so 0.28 plus 0.24 should be 0.52, or 52% of your players or athletes should be either basketball or swim. Easy enough. Okay. Once again, they needed to be mutually exclusive. So they're mutually exclusive because they can only play one sport. You didn't have any basketball players and swimming players at the same time. All right. So now we talked about that. Now we want to look at, okay, what is the situation if we do have some overlap? What if it can happen at the same time? So what if 2 events can occur at the same time? Let's figure out what we need to do for this. So let's say I have my 6-sided dice again. Always going back to this little dice. I'm going to roll it, and I want to find either an even number or a multiple of 6. So what are my even numbers I can get on a 6-sided dice?
2, 4, 6, 4.
2, 4, 6. What are my multiples of 6 I can get?
6. Yeah.
Those would be factors, though. Multiples mean 6, 12, 14, or 18.
5.
So 6 is my largest, it's my smallest multiple, it's my largest possibility I can get on my dice. So 6 is the only possible multiple I can get. Are we okay with that? So, if I want to find the probability of rolling a 6, or getting an even number, or getting a multiple of 6, it should just be probability of an even number plus probability of getting a 6, right? Just put those added together. So my probability of getting an even number is 3 out of 6 options. probability of getting rolling a 6, or getting a multiple of 6, is 1 out of 6 options. So in total, that should be 4 out of 6, right?
What do these two?
Even number, sorry. Typically inside the parentheses, you just create some sort of thing to help you relate it to whatever the event is or relates to the event. So I just said that event is rolling an even number, so I said E for even. This event is getting a multiple of 6, so I said 6. Is this right?
So, but why didn't you trust it?
Well, we said on the last one, right? You take the probability of each of them and add them together, right?
But that's a,
Wait,
but this one's
six
overlapping.
is even number and a multiple of 6.
No, but this is if two events are occurring at the same time, so then it would be the other, and the.
Well, that's if we're looking for both events occurring, or if we're looking for both events happening at the same time. This is just saying if the events can happen at the same time. So if it's possible. So if we're looking for the probability of A union B, that's if you're looking for the probability of both of those. This is just saying it's possible. It's not saying we're looking for it, or it's just possible to happen. So we know it's possible for events to be overlapping, but it doesn't necessarily mean we're looking for it. Is that? But this has to be right, right? Because I have 2, 4, 6, 6. I have 4 possibilities, right?
And it's 6, it's like the same thing. So it's just 3. So yeah,
Because we counted it twice. So whenever you're trying to find the probability of 2 overlapping events, of either or, whenever you're coming back to that or statement, and you're looking for the probability of or, but they can overlap, we always have to subtract by the intersection of them. The probability of getting an even number and the probability of getting a multiple of 6. So you always have to put that subtraction there. Because if we just count like this, we're counting 6 twice. We're counting that number twice. And so in order to watch out for that, in order to negate that, we subtract by that overlap so you only count it once. And so we would have to subtract by our overlap, which our overlapping on this one is just, we have a 6 in each. So that's our overlap. So the 1 over 6 is the probability of getting that overlap piece, which is just 3 out of 6, which should be the correct answer because there's only 3 numbers, 3 distinct numbers. So now,
If you already used
because rolling a 6 and rolling a 6 are the same thing. So I'm counting that twice, which I'm really throwing in an extra answer in there, which shouldn't be that way. So now, anytime we encounter the probability of an or statement, anytime we're using that union, the probability of this or that, it's now always going to be the probability of A plus the probability of the second event, B minus the intersection of the 2, minus the and statement of the 2. The reason this still works for mutually exclusive is because we said if 2 events are mutually exclusive, there is no and. So it was just 0. So it wasn't changing the equation at all, and that's why it worked for all those problems earlier. But now, if we do encounter, and there is possible to get that and in there, we have to remember to tag that piece along. Okay on this? So let's look at another example. Yeah, my letters out of here. So A, let me rearrange them. A, B, B. Okay. I have a bag with first 7 letters of the alphabet in it, A through G, all thrown in this bag. I want to find what is the probability that if I randomly reach into this bag that I will get a letter from the word face or, throw my favorite union in there, a letter from the word face or a letter from the word cat. What is my probability of getting a letter from the word face or a letter from the word cat? If I think about it, face has 4 letters in it. All 4 letters are in that. So A, E, or F, A, I'm sorry, I'm not even saying the right letters, C, and E. These are all in the word face. cab has 3 letters in, or sorry, so this probability would be 4 out of 7 is my probability of getting face. Are we okay on that part? Probability of cab is C, A,
Who would overlap to do a,
B. So probability of cab is 3 out of 7. So once again, probability of the or statement, face or cab, is or cab. Is that probability of the first one plus the probability of the second minus the overlap. So my probability of my first one we said was 4/7. Probability of my second one is 3/7. And I have to look at that overlap again. Well, I had 2 letters out of my 7 that overlapped into both face and cab. Minus, what am I make suicide right now? I had 2 out of 7. So if I add all these together, 4 plus 3 minus 2, all over 7, gives me 5 over 7, or whatever that percentage is, or that decimal, 0.71. Now another way we could think about it is, well, out of all my 7 letters, 5 of them are the only ones that I use. And so 5 out of 7 would be another way. So some of these examples we're doing right now might be pretty easy to solve without using these formulas. But when we do encounter these harder situations, when we do encounter these harder formulas, or when we do encounter harder probabilities, it'll be helpful to have these formulas ready and know how to use them, rather than just having to try to think, okay, what's my overlap, what's my probability of my first event, what's my probability of my second event, and have to scramble through that. All right, okay. I want to look at one last thing, and then we'll do a quick recap, and then we'll call on. All right, similar to the last one. I have a bag with each letter of the alphabet in it. I want to find what's the probability of picking a vowel, or probability of getting a letter from the word math. The probability of getting a vowel or
including one.
math. We'll say y is not a vowel. For this case, we'll say y is not a vowel. How many vowels do we have? 5 out of 26. How many letters do I have in the word math?
4.
Sure. So the probability of the word math is 4 out of 26. Do I have any overlapping letters?
1.
A is a vowel and it's in math, so we'll have to subtract A out of 26, or 1 out of 26. So 5 plus 4 is 9, minus 1 is 8, so 8 out of 26, or if we divide that, we get something, 0.3. Doesn't say right. 8 out of 26 is 0.31. Okay. So we round up. So we talked about a lot today. We covered a lot. We talked about independent events. Independent events were 2 events that did not affect each other. Did not affect each other. So that was like flipping the coin and rolling the dice at the same time. They were independent. They didn't affect each other. We talked about the intersection, probability of A and B occurring. That was our and word. We said if the events were independent, that was the probability of A times the probability of B. I'm sorry about my pen. Probability of A times probability of B. That was only if they were independent was the intersection just a multiple of the two. We talked about mutually exclusive. So mutually exclusive could not happen at the same time. Not happening at the same. Or another way of thinking about it, there wasn't any overlap between the two. There's no overlap between the two. So because the probability of A and B, they can't happen at the same time, that was 0, we said. And then the last thing we said was, what happens if we run into an or? What happens if I want to find the probability of that or that other situation? Good, we added them together.
Then you have to.
Yes. So we find the probability of each of them, add it together, and then subtract what was the overlap between probability A and probability B, intersection. Good. So I know we covered a lot today. Tomorrow we're going to look at some charts, figure out how we call from charts, and then Friday will be a practice day. There were a lot of probabilities that we done. Good job.